Okay. Well, I'm going to hope it continues to record here. If it doesn't, you can look at the notes. But let's go ahead and talk about what we've got going on this week. We've got a quiz on Friday. There's a help session on Thursday at 7 p.m. on Google Meet. If you want help before the quiz, that link is in the syllabus. And like I've said before, there's a copy of the electronic copy of the syllabus. You could just click it there or copy and paste it there or whatnot. You can also get help in the tutoring center if you want, if that works for you. Let's see, what else do we have going on? There'll be a homework due Friday morning at 7 a.m. As usual. That will be on Achieve, as will every homework or almost every homework from here on out. Yeah.
I think that one says it's due tonight.
Did I mess up with it? The one that was today is due tonight, so I messed up on whatever the date was or the time was for that. So if it says it's due tonight, it's due tonight. I'm not going to go in and override it at this point. But the one on Friday, I'm aiming to have these due before class. So that'll be due at 7 a.m. And don't count on me forgetting to hit the time button. I thought I got it last time, but may have missed some sort of checkbox. All right, any other questions or comments on stuff in the class? All right, then we're going to move on today. First of all, let's kind of review one of the really important questions for chemistry that or one of the really important concepts in chemistry that I talked about last lecture right at the end, and that's what a mole is. I'm going to remind you that a mole is a counting unit. Okay, and so we could say 1 mole is equal to 6.022 times 10 to the 23rd things. All right, and this is so important that I'm certainly not going to caret that. Let's go ahead and do that for real, because moles are super important in this class. All right, and so we should be able to convert between moles and grams. Remember that the special thing about a mole is if you have that many things, where things for chemistry would be, let's start with atoms, that 1 mole, or 6.022 times 10 to the 23rd platinum atoms, is going to have a mass of 195.08 grams. Okay, that's why we use that unit. It's also a really nice unit because it's about a handful of stuff. Okay. Now, as we care more about chemical waste and things like that, and things have become more precise, actually you don't do much with a handful of stuff in chemistry anymore. We work with smaller volumes. But people used to work with about that much. So let's talk about using that then. So I could ask a question, okay, and then in terms of molecules, what you would do if you had a mole of a molecule is you'd add up all the atoms in the molecule, and you'd take each, if I had 2 calcium atoms, I'd take 2 times 40, right? Plus if it was with 1 oxygen atom, I don't think that ever happens. Let's do it this way. If I have 1 calcium atom and 2 oxygen atoms, no, it's 1 oxygen. Let's do an example. I'm thinking about, and a little bit later in the course, you'll get the reactivities down. You realize that when I tried to put more than 1 oxygen with 1 calcium, it wasn't going to work. So let's say we have a compound. Let's say it's magnesium, and I'm going to introduce you to this. We've talked about this parentheses thing before, magnesium hydroxide. Okay, looking at the parentheses and thinking about what you know from math, how many magnesiums does this compound have? 1. How many oxygens?
2.
2, right? Because it's 2 times everything inside the parentheses. So 2 oxygens, 2 hydrogens. All right, so we can use our unit conversion here. We could say how much does 3.5 moles of magnesium hydroxide weigh in grams? And more correct would be to say, what's the mass of 3.5 moles of magnesium hydroxide? Weight is a force, but we use it as a mass as well, often, and at least just in terms of general talking about it. So it's okay for chemistry here. All right, so how would we do this one? Well, I've got, what's my given? Oh, I forgot periodic tables. What's my given? 3.5 moles. It's the only thing up there, right? My conversion factors, look at this. They're periodic tables down here. You go ahead and just pass these around, especially, I'll do it over here. Sorry. We'll start over here because these folks need it more than you guys do because you're closer to the periodic table. But there are plenty, it'll get around to everybody. Okay, well, how am I going to get to grams? What's my conversion factor going to be? So I'm going to start with 3.5 moles. And because all I'm working with is magnesium hydroxide here, I don't have to say that in terms of my units for canceling. And then I'm going to have some conversion factor that's going to be 1 mole of magnesium hydroxide. Here I'll say it because it's going to be specific. It's going to weigh some number of grams. How do I figure out how many grams a mole of magnesium hydroxide weighs? The mass is. I'm going to add all the masses and I'm going to take them off the periodic table, right? So it's going to be equal to, and I think I'll stretch this out and do a second equals here. It's going to be 1 times the mass of magnesium. And actually, let's do this. 1 times the atomic weight of magnesium. Okay, plus I have 2 oxygens, you guys said. So 2 times the atomic weight or atomic mass, no, it's weight, of oxygen, plus 2 times the atomic weight of hydrogen. All right, so now I can start filling it off the periodic table. Let's have me not do all the work here. What's the mass of magnesium off the periodic table? Somebody over here. Yeah. Did you say 24.305 or is it 3.1 on yours? Yeah, they can be slightly different, but it was 24.31. That's what we'll use. 24.31. Okay, so they've just rounded differently. It's okay. So how about oxygen? Somebody else over here. I've got this one memorized. You got 16.00. How many sig figs are they giving us? 16.00. So that periodic table, whichever one you got, has two places past the decimal point, probably for everything. And that was a mixture of things I picked up. So we're going to say 16.00. And don't worry if your sig figs off the periodic table are slightly different than other sig figs. Let's see. I'm going to run out of room here. Go ahead and move this over. And you're welcome to write on these periodic tables and things. What I'll do is I'll bring another set. If I want you to use a periodic table, I'll bring you a clean one. I'll put a clean one on the back of the quiz or something like that. Maybe not on the back of the quiz because that slows you down. You have to flip it over. All right, how about hydrogen over here? Yeah. 1.01. All right, and so we can go ahead and multiply all those things through. Like I've said before, try and get used to what your calculator does. Because once you learn what you can trust it for, then you can move faster.
All right, I got 58.33. Everybody get that or something pretty close? Okay. So I'm going to just write that, what was that, 58.33. And we could really trust that to two significant figures there. We'd end up with three significant figures out of that, but then we're adding, and it's to that many places, so we're good. Okay, so it's going to be to two significant figures because I'll get three significant figures out of this, but 2.02 has two past the decimal point for when I add, right? And all the other ones will work for that as well. Why don't I limit to one significant figure because of the two? Yeah, it's an exact number. It's a counting number, right? Okay, so this is our conversion factor. Let me put them all next to each other. 1 mole magnesium hydroxide. Sometimes I'll leave the E off the mole. That's actually the correct abbreviation. You get to save one letter. Not a great abbreviation. And that's equal to 15.33. I didn't include my units over there. Grams of magnesium. Okay. So now we can scoop, now that we have our conversion factor, we can scoot up here. What goes on the top here? Grams or moles? Grams, because I want to cancel my moles, right? Being able to cancel stuff, that's how this works. That's how this process works right here. So 58.33 grams, 1 mole. And so put that in my calculator, 3.5 times 58.33, okay. And I get 204.155 grams, but that's not going to be correct sig figs, right? How many significant figures here in the answer? 2. That's correct, because this has 2 here. That's a measured number. It's not a counting number, right? 3.5 moles. The number of moles of something is, the number of moles of something, unless it's coming out of a chemical equation, is going to be that. So that's clear. That's it, especially since it's not an integer. All right, so then that's gonna become 200, and I'll underline that 0 to make it significant. 200 grams. Questions on that process? Okay. We can do the same sort of conversion with particles. So if you remember, so I just told you that a mole is 6.022 times 10 to the 23rd things. So we could take our magnesium thing again. Actually, let's do this kind of the reverse, I think. So what I'm going to do is, let's say I have let's say 4.5 times 10 to the 22nd sodium atoms. By the way, sodium, you know which one it is yet? I'm not going to really test you on elements, outside of the fact that we're going to have to name things eventually, right? I'm not going to say, hey, name all these things on the periodic table. I will say, name this compound, draw the formula for the compound. Yes. Na, right, Na's tough. Na's tough. I think these come from Latin, which is why we get these different abbreviations. It's whatever sodium was in Latin. Okay, so I have that many atoms. Let me go ahead and get this superscripted. How many moles of sodium atoms do I have? Go ahead and set this one up. I'll remind you of your conversion factor, and I just told you what your conversion factor was, right? That this is going to be the conversion factor, but 1 mole is equal to 6.022 times 10 to the 23rd things. Where for us, things could be anything, but things for us is going to be atoms or molecules. And I want you to get your calculator out, which you should have, right? And let's practice using the exponential functions, because there's some common mistakes that get made here. Okay? Your calculator, actually, get your calculator out, maybe try it. I'm going to shut up for a minute and let you set the problem up, and then we'll talk about it. Okay, let's go ahead and talk about it. We're gonna set this one up. So what I've got is a given is 4.5, so you should have set it up like this. The given's 4.5 times 10 to the 22nd atoms. Pull this down to get myself a little more room. And then that's time to my conversion factor. This is my conversion factor. What goes on top? What's things, by the way, in this problem? Atoms. Okay, so things becomes atoms. What goes on top? 6.022 or 1? 1. So 1 mole. And you can do this. I like to put the equal sign sometimes, like turn the equal sign on its side, is equal to 6.022 times 10 to the 23rd atoms. And then I'll get the number of moles out. All right, let's practice with our calculators. So you may have different sorts of calculators. I don't want you guys to have programmable calculators in here, but I might just let it go. I don't know that I have the energy to chase that down. And I'm giving you all the equations in class. So you should have a key that goes EE on here, right? On your calculator. So what I want you to do is learn to use that EE key. Okay? That's going to save you time and it's going to prevent errors. So the way I would put this into the 6.022 times 10 to the 23rd into my calculator is EE equals times 10, essentially, to the. Okay? So in other words, I'm going to put 6.022 and I'm going to press EE. Okay, and then I'm going to put 23 into my calculator. Does that make sense? So let's all try it. And if you haven't done this before a bunch, it takes a little getting used to. So I really recommend you practice it. Practice along in class, and then you can ask me, you can come up afterwards if you have problems, and I can help you out with your calculator. But all right, so I've got 4.5 EE to the 22 times 1, right? Times 1 divided by 6 point, oops, I didn't press my divide or something. 4.5 EE 22 times 1 divided by 6.022 EE 23. And what I get is 0.0747, more numbers. So I get 6.07472, etc. numbers, moles, right? Because my atoms are on the top and my atoms are on the bottom, so they cancel. And so I end up with, I've got to make that into sig figs. How many sig figs in this problem? 2. We've got that 2 that's measured up there at the top, beginning. So 0.075 moles. Everybody get that? If you didn't get that, if you put that in your calculator and it didn't work out that way, please come talk to me. All right. And we also have, keep practicing as we go, because we had an EE on the top and an EE on the bottom. So if you're making one of the common mistakes, it's possible they'll cancel, right? It'll cancel on the top and cancel on the bottom. By the way, I keep forgetting to announce this. I realized these were up there. There is tomorrow a welcome party from the chemistry club. So if you're really interested in chemistry, feel free to come to that. It starts at 5, but at 4, there's actually 4:30. I'm sorry. There's actually a first half hour for freshmen. A welcome for freshmen if you want to come even earlier. Okay. There'll be a bunch of faculty there, members of the club, and things like that. I'm going to go pass these around in case you want to take pictures of your phone. It's completely optional, but wanted to let you know it's happening. All right. Let's try. I want to try one more thing here. So we haven't done any double conversions with these. What we're going to do is do one more example, a more complicated example, before we move on. And so we have a conversion that can get us from grams to moles, right? And we can get from moles to particles, or we can get from particles to moles. You see, moles is kind of, what I like to do is call it the mole freeway. You have to get on the mole freeway to get to everything, okay? So we can go through moles to convert between things. So if I want to convert between grams to particles or particles to grams, and we'll have more stuff like that, just like this, more of these, I have to go through moles to get there. Okay? I'm saying that in its words doesn't really make a lot of sense, or it's maybe not going to stick really well. So let's do an example. So if I have, let's make it not two significant figures, 3, 4, 5, 6, 7. Grams of water, how many particles of water do I have? Okay, so what I've got is, what's my given? All right, so 3.45, right? So I've got 3.4567 grams of water. And I'm going to actually go ahead and just put the water in, because eventually we're going to be converting between different compounds. So I've got that many grams of water. And now I need to get to particles, right? Molecules is our particle. I should have said molecules. But so it's molecules. And so I need to go through moles to get there, because I don't have a grams to particles conversion, okay? It's going to be different. Grams to particles is going to be different for every single compound, but moles to particles is always the same. It's always 6.022 times 10 to the 23rd. All right, so I know that conversion factor, right? I went up to the top of my test or quiz and I looked up 6.0223, because that's actually a number 2, times 10 to the 23rd. And I'll go ahead and say molecules here. Things. Okay, and then I'm going to need to get to moles from grams. How do I do that? What do I use? I'm going to use the formula weight of water, right? Right? So 1 mole, I'm going to put it down here. I'll put it down here because we're going to string it out. So 1 mole of water has how many hydrogens and how many oxygens? Right, so I'm going to do 1 times the atomic weight, or 2 times the atomic weight of hydrogen. Plus 1 times the atomic weight of oxygen. All right, so 2, go ahead, I'll give you 30 seconds to fill out the rest of that, and then I will. Use your periodic table. Start getting used to pulling these things off your periodic table. Okay, so it's 2 times what? 1.01, and then 1 times what? 16.00. Okay, all right. So that's what we've got there, and then we'll go ahead and put it in our calculators, multiply it through. 2 times 1.01 plus 16.00, 18.02. Okay, and that's going to be grams of water. So that's our next conversion factor right here. This is equal to this. So I need to go from grams to moles. What goes on top here? The 18.02 grams or the 1 mole? 1 mole, right. 1 mole H2O, 18.02 grams water. All right, grams of water cancels with grams of water. Now I need to get to molecules of water. So now I'm using this one. What goes on top? The molecules, yeah, because the moles need to go on the bottom. 1 mole of water contains 6.0223 times 10 to the 23rd molecules. I'm going to write it out. I could have said particles because that's what I said in the problem to begin with. You would have gotten full credit for either, the way I wrote it. Okay, so I'm going to put this in my calculator. And please follow right along and do this with your calculator so we can catch any calculator errors you have. I'm going to take 3.4567. I'm going to multiply it by 6.0223 E23. And I'm going to divide that by 18.02. All right, and so what my calculator is giving me is 1.1582, etc., times 10 to the 23 molecules. Okay, excuse my bad writing there for that. And so we want to put that in correct significant figures. I had a bunch of those, 5 there, right? But here, I took this off the periodic table. We know if we look at that periodic table that they're rounding some, right? So I'm going to take this as 4 significant figures, okay? And then I've got a bunch more. So I'm going to go to 4 significant figures with that, and I went 1 more than I needed to. I'm just going to go ahead and erase this one. And I'm going to go ahead and circle our answer because we've got a lot of stuff going on here. Questions on that process where we use 2 conversion factors? Okay, we'll use 2 conversion factors a lot in this class, and we will often do a lot of things where we need to get from one thing to another, where we have like grams on this side or milliliters or something else, and always think, almost always in these problems, or very often, you're going to have to go through moles to get there. Yes?
So it's kind of like a separate thing. I put the exact same thing in my calculator, and it came out as 1.1552.
1.155.
So mine.
You got the same one?
10 to the power.
All right, well, I'm going to go ahead and it did the 5 round. What was it? 1.552?
Yeah.
All right, well, I'm getting 1.1552. Well, I'm getting old up here. Possibly I looked, and my calculator is actually having a little bit of a seizure as well. You can't see it, but so maybe that was an 8 on my calculator. I'm going to guess since 2 of you put the same thing and got the same thing that I read it wrong. Other questions? Okay, so if I was grading something on a test, and let's say I did that wrong on the answer key, I mean, what would happen is I'd grade a number of tests or quizzes, and I'd see that everybody else had a different answer, and then I'd go check it again, right? But if I didn't catch that, if you put something in and you got something different, you're always welcome to come back and talk to me about it, and we can fix it, okay? For that, you wouldn't like lose all credit. You'd lose like 1 point for rounding, maybe, okay? All right, so we're going to move on here. That was a complex example. There will be examples like that on your homework. Please come get help if you want more practice besides that. It's going to be a homework like the last homework was, now that I kind of learned how to do them, where everybody can get full credit. If you get stuff wrong, you'll just get more practice, okay? We're going to move on then, and we're going to start talking about light, and we're getting into the next chapter, chapter 3. We're talking about light and the quantum mechanical nature of the atom. All right, so let's start off talking about light. So light can be a wave or a particle. All right, so when we talk about light being a wave, we don't really give it a name. We just talk about a wave. But a particle of light we call a photon. And whether you treat light as a wave or a particle depends on the situation, whatever works best, kind of, okay? And like I indicated last lecture, when you get to quantum mechanical levels of things, when you get really, really tiny, the size of the electron, okay? Less so the size of a proton. So you don't have to get much bigger than an electron before you kind of get out of quantum mechanical, but if you get, what do these work? All right, so, but when you get really, really tiny, things start behaving in really funny ways, okay? You can think of light as a particle, but it's kind of everywhere at once, okay? And things act like you can know where that electron is. If you measure it, suddenly it knows where, you know where it is. But until you measure it, it's everywhere. It's really weird stuff. All right, but it explains things well. It may not actually, in thinking about it that way, may not actually reflect what it really is. And so when we think about a wave, actually light as a wave, actually let's not use this picture just yet. Let me draw one. All right, when you think about waves in the ocean, not the waves you see at the beach, but waves when you're out from the beach where they're not crashing, what do they look like? If you looked at a wave from the side, it would look like this, right? Sort of. Okay, you might have that. And this wave has properties. It has a wavelength. A wavelength would be the distance from any given part of the wave to the same part of the wave again. So I could take the crest to the crest. I could take the trough to the trough. I could take something in the middle. But this is my wavelength. And this is how we picture waves as well, waves of light. But this would be, in ocean, they wouldn't be that high, right? This would be the exaggerated cartoon waves where the boat's going up and down those. But the amplitude there would be different. We can also talk about the amplitude of the wave. So how high from top to bottom, all right? We can think of the frequency of the wave. So this wave is moving, just like waves in the ocean, they'd be moving past, right? All right, so if we had our eye here and we were watching the wave, let's pretend this is our eye, do some eyelashes, okay? That's why I don't teach art. And we've got eye there, and the frequency is how many waves go past per second. All right, how many waves passed per second here is the frequency? All right, can you kind of picture that? If you were standing on a pier and watching waves go past, you could watch from the top of one wave to the top of the next wave, and then you could divide by how many seconds that was, and then you'd have waves per second. Let me give you there's a new unit here that you may not have seen before. Per second, okay, is what we call a hertz, like the car rental agency. Not after them at all, okay, but is a hertz. So when you talk about waves per second, it's so many hertz would be your frequency. And you may have heard that before if you think about like electricity, it gets talked about. It gets talked about in terms of sound, how many sound waves per second, things like that. Questions on the parts of a wave? All right, so when we picture waves of when light, here's a picture from your book where it's showing this wave. What's going on is you have an electrical field and you have a magnetic field, and they're oscillating 90 degrees from each other, which I'm just going to say right now, which isn't very important, okay? When we talk about light, we talk about it as electromagnetic radiation. So let's talk about that, though. So light, as we think about it, we say it is electromagnetic radiation. All right, and so the electromagnetic force is one of the four fundamental forces in the universe, right? We've got magnetism, we have gravity, right? We interact with both of those. We have actually, there's a strong nuclear force and a weak nuclear force. We're not going to spend a lot of time on these things, okay? But like I said in the other lecture, the electromagnetic force is what we interact with almost everything, right? We've got gravity sticking into the ground. But other than that, everything you do, me pushing my hands on this table, this electromagnetic force, this electrons in me and electrons on the table running into each other at the atoms and keeping me from falling through the table. So we can talk about electromagnetic radiation. When you think of light, you're probably just thinking about the light you can see, but this electromagnetic radiation is a whole bunch of things you've probably heard about. So this is the visible radiation you see. It's like this big on the scale. This is actually it's a scale that has exponents in terms of here we've got the wavelengths for the exponents. The energy goes the same way. We'll get an equation soon enough. You've got all these various things you've heard about. They're all electromagnetic radiation. It's just how long the waves are. All right, so the light we see, electromagnetic radiation, is too small, right? Okay. We'll talk about these wavelengths right here are in nanometers, and we'll talk about that in a minute. But TV and radio waves, they're big. They're at least this big, okay? This big and bigger. So when you think about when you get radio or you watch something on actual TV, which none of us really do anymore, right? We just watch off the internet. But you're sending those waves. When you get those waves going through the air, they're really big waves. When you use the NMR, which you probably do in lab this semester, maybe next semester, it's using radiation to perturb nuclei, essentially. Okay, and it's using radio waves, so it's using big long waves like that. And then we start getting smaller. We get smaller. Microwave. That is actually, it's a big range, but that is actually the radiation that is in your microwave. When you turn on a microwave and you heat up food, it's that sort of radiation. What it does is causes water to rotate faster, and that makes it hot. So your microwaves are really great at working on things that are hot. Infrared is heat radiation. How many people see one of the Predator movies? Okay, I'm too old. My God. All right, so you see these night vision goggles. If you haven't seen anything with night vision goggles, they have people that's looking at things that you're seeing heat. You're seeing in infrared. Okay, and the Predator movies, it's watching in infrared for most of them. All right, then we've got our visible light that we can see in. Then we've got UV light. Okay, you're comfortable with the colors. UV light, that's the light that's beyond what we can see, and that's what gives you a sunburn. Okay, so we're getting up, this is light that actually is about a good wavelength that it can break bonds in molecules, cause them to rearrange, and that's why you can get a sunburn from it. All of these things can interact with molecules in different ways, molecules, nuclei, atoms. X-rays, you've probably heard of X-rays, right? X-rays can knock electrons out of atoms, so they don't break bonds, but they knock electrons out of molecules, and then the molecules are unstable and they rearrange. And the same thing with gamma rays, if a gamma ray actually hits you, right? Actually, they kind of they can go through you a lot. Okay. So that's what light is. Light is this light when we think about it's a piece of the electromagnetic spectrum, which covers a tremendous number of things you've already seen or have heard of. Okay. So if we think about light as a particle, we can think about light having a packet of energy. All right, if we think about it as a wave, it doesn't really have a fixed amount of energy. Energy is kind of in that amplitude. But if I think about a wave and I'm shining it on things, it doesn't really have a beginning and an end, right? And the longer I shine it on something, the hotter it would get, maybe, if it's something that's going to produce heat. But if we think about light as a particle, we can describe it in terms of the amount of energy it has. Actually, I'm going to talk about the wave thing, equation for the wave thing first. So the characteristics of light as a wave can be described with the following equation. And this is that equation. You will use this a lot. If you're taking physics, you'll use it a lot too. Okay, so this is that says the speed of light. These are all different letters for things that we just talked about. The speed of light is equal to its wavelength times its frequency. Okay, so that's what these letters means. This is a lambda. It's a Greek letter. This is what is that? I'm trying to remember. It's a V. It's not a U, but it's a V and whatever that is in Greek. I'm forgetting at the moment, but you could just do it as a V and it would be fine, right? So if you want to do it as a V, don't worry about it. Okay, so we've got this equation, and we can use this to convert between various things. Now, people like to talk about light in terms of nanometers because that's where the length of light is in the visible spectrum. So light we see is on the order of 400 to 700 nanometers in length, and everybody likes to talk about things in something between 1 and 1,000 when you're counting it. So you switch to nanometers. I'm going to start out by just talking in meters, so the first conversion's easy, and then we'll do one make it a little more complicated. But so I could use this, let's say, if the frequency of light is, let's go with 4.5 times 10 to the, gosh, if I remember this, 19th hertz. What is its wavelength in meters? All right, and this is just going to be a plug and chug problem, but I need all my constants and need to put things in the right places. I'm going to tell you that the speed, and you would get this on a quiz or a test, right? I'm always going to give you these things. If you think I've forgotten, you should ask me. And so I've got the speed of light, c, in a vacuum is going to be 3.0 times 10 to the 8th meters per second. All right, and so let's remind ourselves our equation is the speed of light's equal to the wavelength times the frequency. And so I was told what the frequency was, right? There's my frequency, that's going to go here. There's my speed, that's going to go there, and I'm going to solve for my wavelength. So let's go ahead and do that. 3.0 times 10 to the 8th meters per second. And that's equal to whatever my wavelength is. And my frequency is going to be 4.5 times 10 to the 19th hertz. Hertz is 1 over seconds, right? Remember, hertz is 1 over seconds. So now we've got this arranged a little bit differently, but we're doing algebra, right? I can do anything to one side of the equation as long as I do it to the other. Do you see that I have seconds on this side on the bottom, and I have seconds on this side on the bottom? Everybody see that? So what I could do is I could multiply. I could go ahead and multiply both sides times seconds. And this seconds cancels with this seconds, and this seconds cancels with this seconds. I can do anything to any equation in algebra as long as I do it to both sides. Okay? So that's going to be our rule here. So if I wanted to go then I can go ahead and rewrite this, and I've gotten rid of some of my units. So now I have 3.0 times 10 to the 8th meters is equal to whatever the wavelength is times 4.5 times 10 to the 19th, 1 over 1, or nothing. So I have no units over there. So what's that? What does that tell me that my eventual units are going to be on my wavelength? Meters, right? Because that's all that's left. So then I can go ahead and I'm going to divide this by that. I'm going to divide both sides by 4.5 times 10 to the 19th. Divide this side by 4.5 times 10 to the 19th. These cancel, and then I'm left with my wavelength is equal to 3.0 times 10 to the 8th meters divided by 4.5 times 10 to the 19th. No units, right? Because I cancel them. And once again, we have another great opportunity to practice using the EE key. I know I'm beating that to death, but every year there's some students who have a hard time with that. Haven't used it before. It's confusing. It is confusing. Okay, what I've got out of that is 0.666666666 times 10 to the negative 12. What other people got? Okay. So 6.66666, lots of sixes. We're going to round, so I'm not going to bother, times 10 to the negative 12 meters. How many sig figs? 2, right. 6.7 times 10 to the negative 12 meters. Questions? Okay. What if I wanted that in nanometers? What is that wavelength in nanometers? All right, well, I will tell you for your metric conversions, and I will give you these. 1 nanometer, actually it was split, so I'm going to, is equal to 10, let me do it like this. I can do 1 times 10 to the negative 9th meters, or 10 to the negative 9th meters. You guys see those are the same thing, right? Is equal to the 10 to the 9th negative ninth meters? Do you agree those are the same thing? Okay, so I've got that. I've got my answer up here, right? So I need to go from meters to nanometers. So I'm going to start with 6.7 times 10 to the negative 12th meters times, this is my conversion factor. What's going to go on the top? 1 nanometer goes on the top, right? Because I need to get my units to cancel here. Even if it's really obvious, I've said this before, even if it's really obvious what goes on top and what goes on bottom to you, I want you to start using this because the problems will get complicated enough that you need to use this. All right. I can actually be pretty drunk, and if I use this, I don't make mistakes, okay? And I can only be slightly drunk and I start making mistakes left or right. I can actually be at the board without using this. I can be completely sober and I start not making mistakes not using it, okay? It's an absolute lifesaver. All right, so I've got 6.7 times 10 to the negative 12 divided by 1. I said times 10, but I was using my E key automatically. And divided by 1E9 negative. Okay? And I'm looking at my answer trying to decide whether it was right or not. And I get this. And that's all the numbers my calculator spits out. What's my units? Two significant figures, right? But units are nanometers because that's all that's left. Remember, you always have to use units. Questions? Okay, then let's move on and talk about, so that's how we can interconvert between speed and frequency and wavelength. And I really won't ask you about speed. There might be a problem with speed in your book. I talked about this being the speed of light in a vacuum. If you shoot light through water, it goes slower. Okay, water actually goes slower in other substances that aren't a vacuum, but I'm not really going to ask you about it because nobody really ever cares. I'm not promising that the book doesn't have problems on it. I haven't looked at those problems yet. I'll look at them after class. But so generally you just need to know that in science, okay? If you did something very specialized, you might care about other speeds of light. All right, but so there's this interesting thing that goes on, and this is part of how we know that light is has particle properties. If you take a hydrogen atom and you get it really excited, you heat it up, what it will do is it will emit light, okay? And it doesn't emit a long way broad batch of light. It will actually emit very specific wavelengths of light. Okay, and what this is related to is energy levels in the atom. All right, so if we think about this, I'm going to give you the Bohr model of the atom. This pictures the atom not with the electrons in clouds, but as particles kind of in orbits, which is not correct, but it was good at explaining stuff at the time. So let's go back to our helium atom. So it's got to have 2 protons, 2 neutrons in the middle. And if I misrepresent how far away these electrons are, essentially we're going to have 2 electrons in that lowest shell on the atom. Now, if I excite that Bohr atom, in the Bohr model, one of those electrons can get excited and it can jump up to a higher energy level, an orbit that's farther away. And then what it can do is it can come back, but it only has certain allowed energy levels it can go to. So I can bump it up to here and then it can come back to here right? Actually, let's just have it come all the way back down. That'll be simplest, right? So I can excite it and it can go up to there and it can come back down, do it like this. It can come back down to here. And when it does that, it's going to give up the energy that it had to get up to here, and it gives that off as light. Okay? And it could also get excited and get bumped up. Imagine this guy gets instead bumped up to here. All right? It can then come, actually, let me do that in blue. But then when it comes back down, it can come back down to here. And when it does that, it's going to give off light. You see how this is less energy because it didn't go to as high a level? So here we get less energy. Here we get more energy. All right, I haven't actually done the colors right because red is lower energy than green. But if we look at these lines, that's why you get these lines. So this, I'm going to fix my colors afterwards. This is higher energy, right? What's hotter? If you have a flame, what's hotter, a red flame or a blue flame? Blue flame, right. So this blue would correspond to this energy. I'll fix that color. And then this red would correspond to this energy. But it's very specific energies, and you can only have that if light's a particle. Okay? That's what this is about. We will get to the equations for doing particles and stuff next lecture. Yeah, you can keep the periodic tables. And if you lose them and don't bring them next time, let me know, and I'll give you more.